You're standing in a flat, sun-bleached desert where nothing about the surface suggests wealth, and yet beneath your feet lies more gold than any other single place on Earth has ever held. Muruntau doesn't announce itself with glittering veins or dramatic mountains. It hides its scale quietly, so completely that for most of human history, no one suspected what it was sitting on. Even experienced geologists once struggled to believe the numbers, and yet this single deposit, buried beneath the sands of the Kyzylkum desert in Uzbekistan, contains more gold than any other individual deposit ever discovered. What makes Muruntau exceptional isn't just that it's big, it's that it breaks the rules without breaking physics. For centuries, the area was known for turquoise. Traders along the Silk Road passed through without ever realizing they were crossing one of the richest concentrations of gold on the planet. There were no obvious nuggets, no spectacular outcrops screaming for attention. Muruntau remained invisible until the mid-20th century when geology itself had changed. The deposit was discovered in 1958, not by chance, but by chemistry. Soviet geologists were conducting systematic regional surveys across the desert, collecting thousands of samples and measuring trace elements rather than chasing visible gold. What stood out was an enormous gold-arsenic anomaly spread across a wide area. Arsenic is a classic pathfinder element, meaning it commonly travels with gold-bearing fluids. When follow-up mapping revealed auriferous quartz veins at surface, it became clear that this wasn't a small prospect. Even then, the true scale wasn't obvious. Early drilling just kept hitting gold. Instead of pinching out with depth, the system expanded. By the time mining began in 1967, Muruntau was already recognised as extraordinary, though few yet grasped that it would become the largest single gold deposit ever known. Today, Muruntau is mined from the largest open-pit gold mine on Earth, a vast excavation roughly 3.5 by 2.5 kilometres across and more than half a kilometre deep. The pit alone is visible from space, and yet even this immense operation only exploits the upper portion of the system. Gold continues well below the pit floor, transitioning into underground resources that stretch the mine's life far into the future. After nearly 6 decades of continuous production, Muruntau still produces around 2 million ounces of gold per year. That's just under 14 billion Australian dollars worth of gold, and at current rates, it could keep going for generations. That industrial endurance is not an accident, it's a direct reflection of the geology. Most gold deposits fit into neat boxes. They form when mountain building squeezes fluids out of rocks, or when cooling magmas leak metals, or when chemistry quietly strips gold from circulating fluids. Muruntau refuses to be just one thing. It's a geological hybrid, stitched together from multiple processes that normally operate separately and briefly. Here, they overlapped, reinforced each other, and stayed active far longer than they had any right to. The gold is hosted in ancient sedimentary rocks called flysch. Flysch is essentially a thick pile of sandstones, siltstones and shales dumped rapidly into a deep ocean basin by underwater landslides. These rocks aren't glamorous, but they are layered, chemically reactive, and mechanically complex. They were deposited over 450 million years ago, during the Cambrian and Ordovician periods, long before gold ever entered the system. Much later, these sediments were caught up in a collision that built the South Tien Shan mountain belt. That collision folded the rocks, shoved them deep into the crust, and heated them to conditions where they were neither fully brittle nor fully ductile. This zone, known as brittle ductile transition, is one of the most efficient environments on Earth for moving gold. At this depth, rocks repeatedly crack and seal, pumping fluids through the crust like a slow, powerful engine. Muruntau sits right in that sweet spot. But depth alone doesn't create a giant deposit, structure does. Muruntau lies at the intersection of two first-order fault systems. One runs east to west, tied to the closure of an ancient ocean, the other cuts across it at a steep angle. Where these faults intersected, the crust was repeatedly stretched and opened, creating a long-lived dilational zone. In simple terms, it was a natural pressure release valve, a place where fluids could slow down, pull, and react with the surrounding rocks. Add folding to that geometry and things get even more efficient. The fault intersection occurs at the nose of a plunging anticline, a large arch-shaped fold that acts like a funnel, focusing fluids into the same volume of rock again and again. Most gold systems get one shot at this kind of fluid focusing. Muruntau got many. Heat then amplified everything. Around 300 million years ago, the region experienced a massive thermal event. Granitoid intrusions pushed into the crust, heating the surrounding rocks and baking them into a hard shell called hornfels. Hornfels resist deformation, forcing stress and fluids to concentrate along its margins. Muruntau's gold formed within and around this hornfels zone, effectively trapping fluids exactly where permeability and chemistry were most favourable. This is where Muruntau starts to blur genetic boundaries. Some evidence points to classic orogenic gold processes, where fluids are released during mountain building. Other evidence points to thermal aureole gold systems driven by intrusive heat. Isotopic signatures even hint at a mantle contribution, meaning some fluids or heat may have risen from deep within the earth rather than being recycled from crustal rocks. They're all partly right. Muruntau is a hybrid because it borrowed efficiency from every system it touched. One of the most important borrowed advantages was sulfur. Gold needs sulfur to precipitate efficiently. In many deposits, sulfur becomes a limiting factor. Muruntau had access to a nearby rift basin filled with evaporites, rocks formed when seawater evaporates and leaves behind sulfate-rich minerals. When these sulfates were heated and chemically reduced, they produced large volumes of reduced sulfur, exactly what gold-bearing fluids need to drop their load. Fluid inclusions, tiny trapped bubbles of ancient fluid preserved inside minerals, confirm the presence of hydrogen sulfide in Muruntau's gold-bearing veins. They also show a shift from methane-rich fluids to carbon dioxide-rich fluids over time, a signal that the chemical environment evolved in a way that repeatedly forced gold out of solution. Crucially, this didn't happen once. Radiometric dating shows that gold-related activity at Muruntau spanned tens of millions of years. Early mineralization overlaps with magmatism around 288 million years ago. Later hydrothermal pulses continued well into the Triassic, more than 60 million years later. Each tectonic adjustment reopened fractures. Each thermal pulse reactivated fluid flow. Each cycle reused the same structural trap. Most gold systems burn out quickly. Muruntau just kept getting topped up. Mineralogically, the gold occurs in several forms. Much of it is fine native gold, free or weakly locked and recoverable with conventional processing. Some gold is associated with arsenopyrite, an iron arsenic sulfide that can trap gold within its crystal structure. This gives Muruntau a small refractory component, but not enough to cripple recovery. Combined with the deposit's stockwork geometry, where countless small veins permeate large volumes of rock, this made Muruntau ideally suited to bulk mining. That geometry is a big part of why the deposit could grow so large without becoming uneconomic. Instead of relying on narrow, spectacular veins, Muruntau turned entire mountains into ore. There's also a final, often overlooked factor: persistence of crustal weakness. The fault systems that helped form Muruntau didn't shut down after gold deposition. Strike-slip movement continued episodically into the Mesozoic and even the Tertiary. While these later events didn't add much gold, they preserved permeability and prevented the system from sealing completely. Muruntau's plumbing stayed open far longer than normal. Put all of this together and the picture becomes clear. Muruntau is exceptional because it combined the right depth, the right structures, the right chemistry, the right heat, the right host rocks, and, most importantly, enough time. Not just a few million years, but a geological marathon of repeated reactivation and replenishment. That's why Muruntau stands alone as the world's largest single gold deposit ever discovered. Not a province, not a basin, one contiguous system that concentrated thousands of tons of gold into a single geological trap. It also tells us something profound about Earth itself. There appears to be a real upper limit to how much gold can be focused into one place. Muruntau didn't exceed that limit by cheating the system. He reached it by stacking every favourable condition the crust can offer, then letting them run long enough to matter. Nature doesn't follow classification charts. Sometimes it builds something once, perfectly, and never repeats it again. And Muruntau is evidence of this. I hope you found this as interesting as I did, and as always, thanks for watching. Before I end this video, I'd like to give a big shout out to my Patreon and YouTube members. Thank you so much to everyone that helps to support this channel.